Hey everyone, this is Neha and welcome to the Electronics Troubleshooting lecture series. In this lecture, we're going to learn about transistors as switches. So transistor background information, as you can see on the screen, that we have NPN and PNP transistors, and this is the symbol of these two types of transistor. And you know that no single electronic component is as useful and as versatile as our transistors, and there are two basic type of transistors, a field effect transistor and the bipolar junction transistor. In field effect transistor, they are operated by controlling the depth of a conduction channel between the source and the drain by varying the charge on the transistor gate, whereas in bipolar transistor they are operated by controlling the current from emitter to collector by the magnitude of small current through the transistor base. So in this lecture, we're going to focus just on bipolar junction transistor, NPN and PNP. And you are already familiar with the symbol of NPN and PNP transistor. In case of NPN, the direction of the current is indicated outward. And in case of NPN, this direction of current is inward. And also notice that both the collector and the base are more positive than the emitter for NPN case. So this is positive when you compare with the PNP, where in PNP this is negative and the base and collector both are negative. And you also know that these transistors, they can be made up of germanium or silicon. Silicon transistor, they are pretty famous and mostly used in many applications compared to the germanium one. Germanium transistor, they are used in special application. So for in this lecture, we're going to assume that our transistor, which we are using in all the examples going forward, they are of silicon based. Okay. Now, next is transistor model. So our transistor model is an equivalent circuit of an ideal components which behaves approximately like a real transistor. The model for NPN transistor I have shown here. So this is the symbol for NPN, which you already know, and this is the transistor model for NPN transistor. So this is the case when the transistor is saturated, and when a transistor is in the saturated mode, and this is the case when the transistor is in cutoff mode. Okay, so the base and the emitter leads. They behave like an ordinary silicon diode with the anode at the base and the cathode at the emitter. So thus the current flow from the base to emitter takes place, but it cannot take vice versa, which means going from emitter to base. So in order for the current to flow from the base to emitter, this base must be at least 0.7 volts, and that's for your silicon. So when this is 0.7 volts more positive than emitter, then only the current flow can take place. And when there is less than 0.7 volts from base to emitter, then what will happen? Your basically diode will behave as a reverse bias, and then the base current is going to be 0 milliamps. So all of this follows directly from the way an ordinary silicon diode works. And from collector to emitter, there is a switch you can see here, which is either open or closed. So when it is closed, then your transistor works in the transistor mode. When it is open, then it works in the cutoff mode. So here you see this big current. We're going to talk about this big current later on in this lecture and what it is. And just for now, understand when the base current is when you have some base current, and this base current basically controls the transistor When the base current is big, the switch is closed. And when the base current is 0 milliamps, then what will happen? The switch will be open. Okay. So thus the collector and the emitter leads, they either appear as open circuit or a short circuit, depending on the value of the transistor base current. So when the switch is closed, the current so the current flows from collector to emitter due to the lead polarities. The collector must be positive and the emitter must be negative. And when the switch is open, then no current flows, which is obvious because there will be no current flow through this open portion. The same is applicable to PNP. So previously we saw NPN. Now this is PNP. And you know that the arrow of the current goes inside the base, and these two are the transistor model. This is in case of saturated mode, and this is in case of cutoff mode. Okay. So it's the same thing, only the current direction is going to be different, similar to the previous slide you saw. In this case, this is going to be your IB current, which is going towards this direction, and the current flow is from this emitter to collector, because this is positive compared to this. And same with this, you will have when you have 0 milliamps, that means your switch will be open. And now let's see next, transistor cutoff and saturation. So a transistor is set to be at cutoff when its base current is 0, and thus its collector to emitter switch is open. Okay, and remember that a 0 base current means 0 collector current, means 0 emitter current, means all the currents are cut off in case of a cutoff mode, right? And in case of a saturated mode, what happens when the collector to emitter switch is closed, as you saw here, when the collector to emitter switch is closed, and this happens when the transistor base current is large. And you can look again at these two real models and notice that the voltage from the collector to emitter must be 0 volts when the switch is closed. So in this case, when the switch is closed, the voltage from collector to emitter is 0 volts. Okay. And this is an alternate definition of transistor saturation. Remember, a saturated transistor has a potential difference of 0 volts from collector to emitter. So as you can see, because it is short circuit, so your voltage is going to be 0 volts. Okay, and in case of a cutoff mode, what will happen? You will have 0 current, which means you will have 0 collector current, 0 base current. So all the currents are cut off, and that's why you call it as cutoff mode. Okay, so now moving on here. So we talked about the big base current. So in a saturated transistor, it must have a big base current to turn the switch on. But how big is that current should be? That's the question. And that's what I mentioned here, I big. So how much this I big should be to turn the transistor on? So if you suspect that the transistor is saturated, then analyze the circuit using the saturated transistor mode, then multiply the base current by 20. So 20 is the gain. Okay. So if this value is greater than the current flowing through the collector lead to the collector lead, then the transistor is saturated. So if it is not clear right now, we are going to see a couple of examples, and hopefully there it will be clear. So as you can see here, this is what I mean. 20 IB must be greater than IC, where IB is the base current and IC is the collector current. So if you have if your current base current is multiplied by 20, and if that current is greater than the IC, then that means your transistor is in saturation mode. Okay, so Now, moving forward to this example. So base emitter diode in this case is forward bias. So there is 0.7 volts across it, and that will leave 14.3 volts here because we are taking the 15 volts supply. So maybe let's move on to this circuit, and this is the transistor model of this circuit. And you can see that since this portion, this acts as this is your diode. So that's what is shown over here, 0.7 volts. So if this is 0.7 volts, then this is going to be your 14.3 volts across R1 by KVL. If you apply the KVL, that's what you are going to get. So the base current is going to be 1.43 milliamps. And this means that there is a base current. So we will assume for the moment that transistor Q1, let's say this transistor is saturated. What does that mean? It means that if you multiply 20 to this base current, then it should be greater than, if it is greater than 50 milliamps, then your transistor is in saturated mode. So let's assume that it is in saturated mode, but to confirm that, we will have to follow the steps. So if this transistor is saturated mode, which means the closed switch, we saw the model, and from there we have drawn this, and this is the switch here. So that means the switch is closed. Then the collector potential is going to be here 0 volts. Okay, so there are 15 volts across R2. So across R2 you're going to get 15 volts. So the collector current is going to be your 15 milliamps. Now let's check to see if our transistor is indeed saturated. So what we're going to do, we're going to multiply 20, which is the gain, and your beta. So we are going to multiply the beta to this base current. So if you multiply 20 to 1.43 milliamps, then you are going to get 28.6 milliamp. And that 28.6 milliamp is larger than your 15 milliamp. Okay, so what is, let me write it down here. Okay, so what I mean is you multiply 20 with 1.43 milliamp, and that will give you 28.6 milliamp. Okay, and this current is greater than your IC, which is your 15 milliamps. And if this is the case, then that means your transistor is saturated. So that means transistor is saturated. Okay, so that's how you do it. Now let's so we can now finish our analysis. And the emitter current must be the sum of, so the emitter current here, it should be the sum of the current coming from the collector side and from the base side. So we are getting 15 milliamps from here and 1.43 milliamps from here, and that will sum up to 16.43 milliamps if you do the KCL. So two currents are going into this node and one current is going out from this node. So yeah, this is the current, emitter current. Now let's move on to the next example. So here the base emitter diode is forward biased. So there is a 0.7 volts across it, and that leaves 14.3 volts across R3. One thing to notice here, that this is a case of a PNP transistor. If you see this arrow, this belongs to a PNP transistor, and that's why if you compare to the previous circuit, that here the diode was in this direction, and in case of PNP it is in this direction. Okay, so you will have 14.3 volts here. Okay, so the base current is going to be 715 microamps, and this means that there is a base current. So we'll assume for the moment that transistor is saturated, and we'll check if our assumption is correct or not. So if transistor is saturated, then the collector potential, it should be 0 volts, right? Because in saturation mode we know that this switch will behave as a closed switch, so we are going to get 0 volts. Okay, and the voltage across this R4 is going to be 15 volts, and that by applying the KVL, we will get the current here as 29.4 milliamps through these voltages. Because we know the voltages, we can find out the current. So the current across this R4 is 29.4 milliamps. Now we know that to check if our transistor is saturated, what we'll do, we are going to multiply 20 the gain. We are going to multiply the gain to this base current the way we did previously. So we multiplied the gain, this beta, to this base current 1.43 milliamps. So we'll do the same thing over here. So we'll multiply. So after multiply 715 microamp, we'll multiply this by the gain 20. We will get, if you do the multiplication, then you should be able to get 14.3 milliamps, and this should be greater than 29.4 milliamp, which is not true. Greater than 29.4 milliamp. So this is not true. Okay, so definitely not in saturation mode, not in saturation. Okay, so this particular example says that this is not in saturation mode, and so this means that this value is not, this means that we cannot conclude that our transistor is in saturation, and we must leave this problem here. We can neither say that this transistor is in saturation mode or in cutoff mode, because you know that in cutoff mode you get zero currents. So that's not happening here. The currents are non-zero, and neither they are in saturation mode. So you might be tempted to conclude that when Q2 is not saturated, it must be in cutoff mode, but that's not true, because for cutoff mode, the current should be zero. And there are actually three transistor states: saturated, cutoff, and the third one is called neither, which means linear. Okay, so saturation and cutoff are the extreme states of the transistor. When a transistor is used as an amplifier, then it operates in the linear region, which is between these two extremes. So you can say that your transistor is in linear region. Okay, which is the state between your cutoff and the saturation. Now next comes is the driving the base. So in this particular topic, we are going to see how transistor base current controls its on and off action, simply stated. Like in this one, it is the switch is open, and in this state the switch is closed. One thing to note that these two circuits are same circuit. There is some so this resistance has been put strong here. It should be 2 kilo ohm. Okay, same like this one. So this is 2 kilo ohm, this is 2 kilo ohm. So now simply stated, when base current is turned on, the transistor is turned on, and when base current is off, the transistor will be off. So by this example, we'll see, like in the first method, to control the base current of the NPN transistor. This is the NPN transistor. Current is going outside to the emitter side. So in this, when the switch is, so let's see this first one. When the switch is placed in series with the base resistance R1, then the no base current will flows from the switch, because the switch is open. So in this case, your transistor will be off, which means it will be in the cutoff mode. Whereas when the switch is closed, then what will happen? The base current will flow to the emitter, and in this portion you will have 0.7 volts, and you will have around like 1.43 milliamps as your base current flowing in and turning on the transistor, which means it will be in a saturated mode. Now moving on to the next circuit. So this circuit is similar to the previous circuit, but the only difference is that now in this circuit the switch is placed in parallel with the base and the emitter leads instead of in series with the base. Okay, so in this first case, when the switch is open, then your 1.5 milliamps of base current flows, and in that case your Q1 is turned on. Whereas in this case, switch is closed, and when the switch is closed, then the base potential is going to be 0 volts, and this means that the base emitter diode has 0 volts of potential difference across it, and thus no current through it. So this is of course means that a transistor is in cutoff mode, because as I said before, that your emitter current, base current, and collector current, that when it goes to 0, that means your transistor is working as a cutoff mode. So variations on these two methods, so this method and the previous method, which you saw when the switch was in series, and in this when the switch was in parallel, can be used with both NPN and PNP transistors, as well as with positive and the negative supplies. So here the key ideas are that in the first method, when your switch was in series with the base, the switch is when the switch is closed, the base current when the switch is closed, then the base current flows and the transistor is turns on, and when the switch is open, no base current flows and the transistor is off. And in the second method, uses a parallel switch with the transistor base emitter leads, and when the switch is closed, the voltage between the base and the emitter, when the switch is closed, then the voltage between the base and the emitter is held at 0 volts, which prevents the current flowing from the base to the emitter, and thus turning off the transistor. And when the switch is open, in this case the base current flows and turning on the transistor. So now let's move on to other PNP and NPN configurations. So this particular configuration shows that you are using 2N3904 silicon NPN transistor with 15 volts DC supply, and this Q1 transistor turns on when the switch is open. So when the switch is open, then it will be turned on, and in that case your base voltage is going to be 0.7 volts, and IB for this particular case is going to be around 1.4 milliamps. So as you can see, when the switch is open, then IB is going to be 1.43 milliamps, IC is going to be 13.40 milliamps, and emitter current is going to be 14.83 milliamps. Okay, and when the Q1 turns off, when this Q1 turns off, which means the switch is closed. When the switch is closed, then VB is going to be your 0 volts, and all the currents are going to be 0. As I said before, only the voltage across the collector will appear, which is your 13.4 volts. Otherwise the emitter voltage and the base voltage is going to be 0. So how we got this 13.4 volts? We got it from here, because if you see that now here we have the LED. Let's say it's a red LED which is in series with the collectors, and which turns on and off when the transistor is on and off. Okay, so because of this LED, we are getting 13.4 volts. And how we got that? Because if you subtract if you take the potential difference between these 2 points, so this is 15 volts and this LED will have around like 1.6 volts. So if you subtract that 15 minus 1.6 volts, then you will get 13.4 volts. Okay, and that means since it is a 1 kilo ohm resistance, we are going to in that case we are going to get 13.4 milliamps when the switch is open. So that's why you get here 13.40 milliamp as your IC current. Now moving on to the next configuration. So this is a similar circuit but flipped upside down with a negative 15 volts DC supply line. The operation of this circuit is similar to the previous circuit. The only thing that has changed are the potentials. So in this, the current, as you can see here, these potentials are different when the switch is open and when the switch is closed. Okay, so the currents flow from, in this case, from more positive, which means here 0 volts is going to be more positive compared to the negative 15 volts through R1, and here through R2, CR1 and Q1 to more negative potential, which is this negative 15 volts DC. So just as we did in the previous circuit, similar to that, but now they flow up instead of down. Okay, so so here this table basically summarizes all the potential and currents for both circuit for this circuit when the switch is open and when the switch is closed. Okay, so these are the potential VB, VC, VE. So when the switch is open, then we'll get these values. When the switch is closed, then we will get the base voltage as 15 volts, and that in that case VE is going to be negative 15 volts and VC is going to be 0 volts because it's directly connected. There is no resistance here, and that will be cutoff mode and there will be no current, 0 milliamps, and in case when it is open, then we'll get all these values. Now moving on to the third circuit. So this is a PNP transistor circuit with negative 15 volts DC supply, and in this case when the switch in this case your switch is in series with the base. Okay, so Q2 is off when the switch is open, which is obvious from the circuit, and it will be turned on when the switch is closed. And then you will get all these values when the switch is open, then you'll get this. Definitely when the switch is open, then no current in cutoff mode, and when the switch is closed, then it may be in your saturation mode. Okay, now so I'm skipping this circuit because this is a pretty simple circuit and you can do the calculation to verify if this results matches with your calculation. Moving on to figure D, so the same circuit flipped upside down with a plus 15 volt DC supply. Again, the operation of the circuit is similar to C and similar to C, and only this in this case the potentials are different. Okay, and potentials are summarized here, and you know that when the switch is open, then there will be no current, cutoff mode, that's why it's all 0 here. When switch is closed, then you will get these voltages and these currents flowing in. Now moving on to the next is troubleshooting transistor circuit. So this circuit is given, and in this we will discuss some practical transistor troubleshooting techniques. Remember that we are restricting our attention to bipolar transistor used as a switches. So how can you tell if a transistor is good or bad? So first you must know whether the transistor is NPN or PNP. You can find this out by looking up the transistor part number. So like 2N, so for like this 2N3904 in a transistor, and diode data book or their data sheet will tell you whether the transistor is germanium or silicon, or is it NPN or PNP. So its typical use, its power amplification, switching, etc. Its current gain, upper cutoff frequency, breakdown voltage, power rating, and much more information is you can find in the data sheet. So the simplest way to check a switching bipolar transistor is to build a test check, like the ones which is shown here in the previous circuit which you saw. So in those circuits, the LED can then be used to indicate whether the transistor is turning on and off like it should. And if the LED does not turn on and off when the switch is opened and closed, that is, if the LED remains always off or always on, then the transistor is, you can say, it's bad. Now let's analyze this particular circuit. So if you see that when the switch is open, then what will happen? In that case, your Q1 gets the base current, and then it will be turned on. Uh, and this should be checked by multiplying the base current by 20. And then if it is greater than IC, then that means it is in saturation mode. And if it is not, then it will be in linear mode. And so when Q1 is on, then there is a short from the collector to emitter, which should turn the CR2 off. This CR2 is your green LED. This will be off since it is shorted out. And this also means that anode of CR1, so the anode of this CR1 is at ground. So CR1, if it is ground, and this is at lower potential, that means CR1 should be on. So in short, when the switch is open, this switch is open, then in that case, your CR1 will be on and CR2 will be off. Okay, and in that particular case, you will have some voltage across here, VA voltage, which should be some negative voltage, somewhere around like negative 1.6 volts, and your VB is going to be your negative 0.7 volts, and VC in this case is going to be 0 volts, as you can see over here. Now, when the switch is closed, then what will happen? Then that means your transistor is off. Okay, so when the transistor is off, so in that case, what will happen? Your CR1 and CR2, and they both are forward bias, and both will turn on. In short, when your switch 1 is closed, means your CR1 and CR2, they both will be on. And in this case, you will have some very negative VA voltage, somewhere around like negative 4 volts, and your VB is going to be 0, because obviously this switch is open, the switch is closed, so here voltage is going to be 0 volts. And you will have some VC voltage, some negative VC voltage. Okay, so now that the circuit, how it works. So it's the same circuit from the previous slide. So now you know that how it works. So here are some troubleshooting questions which you should ask yourself. So assume switch is open and you measure VB is equals to negative 15 volts. Then what is the probable fault? So you should think about it. If your VB is negative 15 volts, what is the probable fault, and your switch is open? So VB should be equals to, in that case, 0.7 volts, which is equals to your negative 7.7 volts. So the base of the transistor is, in that case, is disconnected, or you can say it has failed open. Second question is, assume switch 1 is closed and you measure, so this is closed and you measure 0.7 volts. What is the problem? In that case, you should measure 0 volts, that when the switch is closed. So the switch is disconnected, or it has, you can say it has failed open. Third question, assume that CR2 turns on when the switch is closed. When the switch is closed, CR2 turns on when the switch is closed and turns off when the switch is open, like it's supposed to do, but CR1 remains off for both switch position. What is the problem here? So in that case, you can say the transistor is turning on and off like it should, and there is a current path through CR2. So it looks like CR1 is either like shorted or something is wrong with the LED. Okay, and fourth question, assume you measure the current through R2. So R2 is here. And you get around like 10.5 milliamps with a switch closed and 9.2 milliamps with the switch open. Okay, so when the switch is closed, then you get 10.5 milliamps. When the switch is open, you get 9.2 milliamps. Is the circuit working properly? So yes, the circuit works properly in that case. Uh, Question 5. Assume that the neither LED lights, regardless how switch 1 is set. List as many fault as you can, which could explain these symptoms. So here are the likely possibilities. Maybe you can say CR1 is backwards, CR1 failed open, R1 resistance is too large or open, uh, R2 is also large or maybe open. Maybe the power supply is of wrong polarity, or maybe you have like zero power, or maybe you have open trace in the CR1 and CR2 supply path. So maybe VB is shorted to the ground. So something like that, those symptoms can be included. And if you think of any more symptoms, you can include that. So if this is not clear, I would say like just pause the video and then see the circuits and see if you are able to answer all these questions. So that's all in this lecture. Thank you so much for watching.